Alright, we're going to go over some concepts from in particular, we're going to look at concavity and trying to find max and min with the second derivative test, and then we're also going to look at the mean value theorem today. So we're talking about concavity, and remember, when you have a function like this, so let's let this be f, the derivative f prime gives you increase and decrease. Alright, so I can see here that I'm going up. Let's give these some numbers. Let's say -1 to, how about 3? I can see that I'm going up from negative infinity to -1, and also from 3 to infinity, because I'm just looking at the picture. And so what that tells me here is that the derivative is positive over those intervals, because the derivative measures the rate of change, and so that's going to be going up. As it's going up, the derivative is positive. Now, between -1 and 3, I'm decreasing. And the reason that is, I can just look at the picture, but what I know then is that the derivative is negative over that interval, because again, the rate of change would be negative, meaning the slope of my tangent line would be negative. It's going down. Okay, now, the second derivative is what tells me concavity. And what the concavity means is basically the rate of change of the rate of change. So look, if I did my tangent lines across here like this, so I'm doing tangent lines, notice that these tangent lines are all sloping up. They're all positive, but they are slowing down as I get close to this value. Once I hit the 0, look, the tangent lines are going negative again, and up until this point they're increasing in their negative value, if that makes any sense. So if I could write the slopes of all these little tangent lines, so let me just make up some numbers. Let's say that's a slope of 3, and here's a slope of 2.5, and this one has a slope of 1, and this one has a slope of 0.75. Here I have a slope of 0. So notice as I'm going, the tangent line slopes are going down. What this tells me is that on this interval, I'll try to use it in red here, from here all the way to about right there, the tangent lines are going down in their slopes. And what that says then is that the rate of change of the rate of change is negative. So if I'm concave down, that means that my second derivative is negative. And concave up would be the opposite of that. My second derivative is positive. Concave down looks like this. Concave up looks like that, like a bowl. So cups and hills and bowls is the way I think about it. Let's do an example of this and just try to figure out what's going on. Now, for concavity, it works just the way we did things for the first derivative. We found, to find increase and decrease, we had to find our critical points. Once we found our critical points, we could find where we could increase and decrease. We're going to do the same thing here for the second derivative. We don't call them critical points. When the second derivative equals 0, let me say it like this. If the second derivative at c equals 0, then c is called an inflection point. Okay, so we do the same thing. We find the inflection points, and then from there determine concavity. Alright, so we're going to find concavity. This is example 6 in the textbook, and our function is x to the 4th minus 4x cubed. You know what? Let's go and find increase and decrease as well, the intervals of increase and decrease. Because we kind of need to go through that step anyway to get to concavity. So I have f of x equals x to the 4th minus 4x cubed. That means my derivative then. And what makes this chapter hard, really, is just challenging our knowledge of derivatives. If you have a hard time calculating derivatives, this part can be challenging. So here I have 4x cubed minus, what is that, 12x squared. That's my first derivative. And then my second derivative, let's go and calculate that, would be 12x squared minus 24x. Okay, so to find increase and decrease, what do I look to? I look to the first derivative. So first I find the first derivative equal to 0, which means I have this 4x cubed minus 12x squared equal to 0. I can take out a 4x squared, and I'm left with an x minus, was that 3? I didn't mean to write subtraction there, that's multiplication. And then so that gives me critical points at 0 and 3. And these again are called my critical points, or we call them CPs. Alright, so to find my intervals of increase and decrease then, I just do a sign chart. I am plugging this into the first derivative. Here are my critical points where I hit 0. And then from there I pick values, test points, just to figure out if the derivative is positive or negative. And I don't really care which one it is. So we can pick something below 0. How about negative 10? Something between 0 and 3. How about 1? And something bigger than 3. How about 100? And again, all I care about is the derivative negative or positive. And the easiest way to do this is to look at the factored version of your derivative. Okay, so for example, when I plug in negative 10 into x squared, I'm going to get positive. Negative 10 minus 3 is negative. So I'm going to multiply those together. That's negative, and that tells me that any x value less than 0 will make the derivative negative. If I plug in 1, I get positive into 4x squared, and I get negative again, and x minus 3, so then I have negative values as well from 0 to 3. When I plug in 100, you can see that we get positive, positive like that. So what this tells me then is that f increases where? Well, this is going down, this is going down, that's going up, because when the derivative is positive, the function is going up. When the derivative is negative, it's going down. So I'm increasing from 3 to infinity, and it's decreasing from negative infinity to 0 and 0 to 3. Okay, so there's our intervals of increase and decrease. Now we just want to look at concavity. And how do we do that? We do the exact same thing, just with the second derivative. So I take my 12x squared minus 24x, set it equal to 0, and I can take out a 12x again. I'm left with x minus 2. So I get x equals 0 and 2. And these may be inflection points. And when I say maybe, inflection point technically by definition means your concavity changes. So I'm worried that at 0, since I was going decrease and then decrease again, I may not have a change in concavity. So 0 may not technically be an inflection point. Let's just check it out. By the way, on these sign charts, I do think it's worth labeling these because it's very confusing sometimes. I've had students in the past get confused. Am I plugging in values into f prime, f double prime, or just f by itself? What's going on? So if you label your sign chart, I think that helps take out that one step of potential confusion. Alright, you know what? We could pick the same test points. They satisfy what we need, something less than 0, something between 0 and 2, something greater than 100. And I'm plugging it into the factored version of my second derivative. And let's see what we get. So when I plug in negative 10, I have a negative for 12 times negative 10. And then a negative again. That gives me a positive. Okay, when I plug in 1, I end up with a positive times a negative. Oh, so there is a change in inflection around 0. Okay, so it is an inflection point. And then when I plug in 100, I have a positive and a positive, which gives me positive. Okay, so what does this tell me? F is concave up. Now remember, concave up is like this. If we're concave up when the second derivative is positive. So we're going from negative infinity to 0 and 2 to infinity. We're concave down when and that again looks like this, like a hill, going from 0 to 2. Okay, and we could say that I have inflection points at 0 and 2. F has inflection points at x equals 0 and 2. Alright, does this make sense? So I can graph this Let's see. 0 is a key point. 3 and 2. So let me start over. So here's 0. And actually, I'm going to mark 4 as well. Why 4? Because if I had set the original function equals a 0, then once you factor it, you get x equals 0 and 4. So that means 4 is an x-intercept, and so is 0. Alright, now also, we didn't mention this here, but if I use the first derivative test, I can see then, since I changed from decreasing to increasing, I have a local, what would that be? If I'm going down and then up, I have a local min at x equals 3. So my value of 3 at x equals 3 will actually be a low point. I'm not going to plug it in, but if you did, I'm just basing this off the book's work, you get 3, negative 27. Okay, so let's see if we can put this together. I am decreasing from negative infinity to 0. I'm decreasing. And I'm also concave up from negative infinity to 0. I'm going down, but I'm inflected upwards, and I hit 0, 0. So something like this. Right? I'm decreasing, concave up, hit 0, 0. From there, I'm still decreasing from 0 to 3, but now at 2, I have some sort of inflection point. So I concave down from 0 to 2, something like that. But then from 2 to 3, I concave back up. Hit that low point. And does my concavity ever change again? It doesn't. I'm concave up from 2 to infinity, so something like this. And I have no more inflection point. So there's a pretty good sketch of f. Notice your first derivative is going to be negative because I'm decreasing. On this span, my first derivative is negative again because I'm decreasing. Between 2 and 3, my first derivative is negative. And then from 3 onward, my first derivative is positive. Okay, again, decrease, decreasing, decreasing, increasing. My second derivative, well, starting out on concave up. So my concave up would mean my second derivative is positive. Between 0 and 2, my second derivative was negative. I can see that because I'm concave down. You're thinking now hill and bolt. Okay. Between 2 and 3, I'm concave up again. That means my second derivative is positive. And from 3 onward, I didn't hit an inflection point. My second derivative is still positive. So there's kind of an overview of how the derivatives relate to the graph. Now sometimes we get confused on what the actual function is doing as far as positive and negative, and that's simply above or below the x-axis. So here I'm above the x-axis, here I'm below the x-axis, I'm below the x-axis again, I'm below the x-axis up until 4, and then after that my function is positive. Alright, so hopefully this connects all of that together. There's one more detail we could add, and that's called the second derivative test. Okay, the second derivative test says, well, let's let c be a critical point. It means I take the first derivative, plug in the value c, and I get 0. Now, if I take that and plug it into my second derivative and get a negative value, let's think what that means. If I have the second derivative, and the second derivative is negative, that means that I'm concave up. But since c is a critical point, that means that when I plug in c, I have a horizontal asymptote. At the location c, I have a horizontal asymptote, so it's a min or a max, but the concavity is concave down. There would have to be the hilltop, right? The hill means concave down. I'm at the high point on a hilltop, or of this hill. So that means that if my second derivative is negative, then x equals c is a local maximum of f. I hope that makes sense. If we flip it around, so this time I have a positive concavity. Positive concavity would look like this. Where do you have your horizontal asymptote on a positive concavity? Down here at the bottom. So if the double prime is positive, then x equals c is a what? A local min of f. And that's what the second derivative test says. Okay, so let's go back to the example we just looked at and see if that's consistent with what we had. Okay, so we said that we had a min down here at x equals 3. So according to what I just said, if I plug in 3 into the second derivative, it would have to be positive. And notice the second derivative is positive here. Where's my sign chart? Here's 3 over here, and we're positive anything greater than 2. My second derivative was positive. It has this bowl shape. My critical point then would have to be an absolute, a local min. And that's what we mean by the second derivative test. Okay, the mean value theorem. So here's what the mean value theorem says. We're just going to let f be a function that is 1 continuous on a closed interval a to b, and 2 differentiable, meaning what? It has a derivative on an open interval a to b. Okay? So if you have that, then there exists a c somewhere between a and b, where when you take the derivative at c, you get f of b minus f of a over b minus a. Or if you do some algebra on this, you could say that b minus a times f prime of c equals f of b minus f of a. What on earth does this mean? And that's a fair question. It takes a little while to read mathematics well. Let me give you a picture. Alright, so here's a and b. Identify f of a and f of b. We identify f of a and f of b like this. Okay? And the question you have to ask yourself is, where did this come from, that relationship? We've actually seen that before, maybe in a form like this, y0 minus y1 over x0 minus x1. That looks a lot like a slope formula, and that's exactly what it is, because and actually earlier in the semester we talked about the secant line. If I connect a to b with a straight line, this secant line has slope m, which is this f of b minus f of a over b minus a. So in other words, the secant line, if you remember, the slope of its secant line is the average rate of change. Okay, so what I'm saying here is I take the average rate of change from a to b. Somewhere in between, there has to be a value c whose derivative equals that average rate of change. The derivative means what? The instantaneous rate of change? Okay, so here the instantaneous rate of change at some point equals the total average rate of change. I think I can draw that in my graph, maybe somewhere right in here. If I take the tangent line, the slope of the tangent line is equal to the slope of the secant line from a to b. So in other words, at that point c, the instantaneous rate of change equals the average rate of change. And actually I think I have another one over here somewhere where I have these tangent lines that run parallel to the secant line. That's what the mean value theorem says. Let me give you an example, and I'll just stick with the book's example. I mean, they have good examples here. So this is example 3 from your text. And here f of x equals a cubic polynomial, and we're going to let a be 0 and b be 2. But we want to find that value c in between 0 and 2 that equals that average rate of change. Alright, so what we're saying then is we want f of 2 minus f of 0 to equal the derivative at c times 2 minus 0. Okay, and I'm using expression here, which is just an algebraic version. It's equivalent to the original expression, right? It just makes our work a little bit easier. So solving for c, I plug in 2 into my expression, I get 8 minus 2, minus plugging in 0, I get 0. The derivative is going to be what? 3x squared, but I'm plugging in c and for x, minus 1, and then 2 minus 0 is just times 2. So I get 6 equals, what is that? 6c squared minus 2, or get 8 equals 6c squared. Okay, so then 4/3 equals c squared. So when I take the derivative, take the square root of both sides, I get, remember when I take the square root, I have to put it in plus or minus. I get 2/√3. But remember, I'm only going from 0 to 2, so that means that I have c to be 2/√3. That is the location. This instantaneous rate of change equals the average rate of change. If I was going to graph this function, it would look something like this. Here's 0, here's 2, something like that. If I take this average rate of change right there, at the location, mine's not really that well to scale, but the location 2/√3, the instantaneous rate of change is parallel to the average rate of change. Does that make sense at all? I hope so. What this can tell you is something like this. I didn't go over this one in class because we just didn't have time, but this is a good example as well. Example 5. So suppose that f of 0 equals -3 and f prime is less than or equal to 5 for all values of x. Here's the question. How large can f of 2 be? So in other words, we know something. We know a starting point, which is f of 0. We know a bound on our rate of change. So this is some sort of governor. Our rate of change cannot be greater than 5. Based on that, what's the maximum possible value that f of 2 could be? So, I mean, maybe this is my starting profit, which is not good. It's negative. And I know that my increase in profit can't be greater than 5. So I have a certain target of mine. Is it even possible to get to that target? How large can f of 2 be? So again, I'm going to look at this equation here. All right, so we're trying to figure out about f of 2. So I can isolate that. This is going to be 2 times the derivative of c, which is going to be -3 plus 2 times f prime of c. Now the thing is, f prime of c has to be at most 5. So this is going to be less than or equal to -3 plus 2 times 5. And so when you do the arithmetic there, 7. That means that f of 2 can't be larger than 7. So if I give you a function, I say, look, f of 0 is -3, the derivative is less than or equal to 5, and f of 2 takes on the value of 10, you're going to be quick to tell me either that function is not continuous or it doesn't exist. Alright, so the mean value theorem can help us with that. Guys, I hope this makes sense. We looked over the second derivative test, concavity, and the mean value theorem. Next time, tomorrow, we can look at limits and infinity. If you guys have any questions on it, let me know. And I guess we'll see you guys tomorrow.